So let me get the camera going here, and you can tell me, I think I know what you're talking about, but.
Well, this particular one was number 4 in my math class, but like I said, I've got question marks
Okay.
besides it.
And when we get finished here, I will go in and look up specific problems y'all are working on that you're stuck on.
So as far as the test for 15, is that?
Test for 15 you will get next Monday night, and you will have until the day of the final to bring it in.
Oh my gosh, so we gotta work on that test while we're on study.
But the reason I want you to work on that test while you're studying for the final is because there is nothing on the final, I mean nothing, that you haven't seen before.
You promise?
I promise.
I swear, it is.
Some of most of the problems on the final exam, most of the ones that you would, that I know y'all would consider to be more difficult.
Are you recording?
Not right, well, yeah.
We need that on tape.
What's that?
You saying this, we haven't.
It's, I just said it.
I want to
And
record
it is recording. It's recording, Tarina.
Okay, because
Okay.
when I come up there and say, because it's honestly, like even on the take-home test, we get them and it's like Greek. It's like, where the hell did this come from? I didn't see anything like that.
Tarina, the take-home test
I'm not one
problems,
that has the guts to say this.
I understand, and I'm glad you do.
Okay.
But the thing about it is that most of the, especially the word problems on the take-home test, those word problems, I actually cut and paste straight out of the textbook.
Well, textbook and what we do in here is 2 different things, and what you go over.
My math lab is the same thing as what the problems are at the end of the chapter.
That exponential thing, we had nothing like that. We had part of that page I told you that I bombed that whole freaking page of the last.
Let me get the test.
No, let's don't get sidetracked. Let's
All right.
go ahead with what we're doing, but.
There is one on the last test. I don't remember for sure the number, but there is one on the last test that I am probably going to throw out for everybody and then count it as a bonus for people that actually got it right, because I wrote the question, and when I wrote the question and then started working on the answer, I realized that I didn't make clear what it was you needed to do to answer that question. I think it was 14.
Oh, thank God, that was one of the.
Is that the one about the toys?
Yes.
Okay, that's the one that and I haven't even gotten to that one on y'all's paper yet. But when I worked out the key for it, I was like, boy, I really messed this one up. I didn't word that very well.
Well, it was
So-
like, and that's the kind of thing I'm talking about. A lot of times what we've gone over in class and done in my math lab and even in our show B and that stuff is, it seems so different when we go to take the test. So if on the study guide, because you told me the study guide for the final would be, please.
You
Please
already,
make it very
you
simple.
have, you have 3/4 of your study guide for the final exam already,
In what? From our tests?
from your tests.
From previous tests?
Yes. The only part you're missing is the last part of the test.
And the right answers.
I'll post the right answers to
Okay.
it
Okay.
when it's due.
Okay, so if we study those previous tests, that will, I'm holding you to that.
Well, I know you will,
Oh, yeah, you know, I will.
okay?
Okay.
Okay, now, basically, and I'm just gonna tell you the way this part works, because I know the part that you're frustrated with. This part says that what you're doing is you're undoing the chain rule, okay? And if this was a chain rule problem to start with, then this should be the derivative of what's inside those parentheses.
Can you turn the light off, please?
Yeah. So they call the way that they do it is they call it a U substitution. Basically, it's like when you were doing chain rule, whatever was inside was the function, and whatever was outside was a different function, but you had an inside and an outside function. And the derivative of the outside function is what gave you this part, the 2x to the third plus 1 raised to the fourth power. And then the derivative of the inside of that function is what would have given you this part. Okay? If you can kind of link it up that way. So if you take this to be the u, not the fourth power, but the u, the thing that was inside, then is its derivative 6x squared dx? And it is. The dx just says this thing in front of me is a derivative. That's all it's doing. So this integral gets rewritten as u to the fourth power du, and all you do to fix u to the fourth power and integrate it back into its antiderivative is you add 1 to the power and divide by the power. And then the derivative, that 6x squared dx, that's du. And it's just saying this is the derivative of that. So it just kind of disappears.
How does it just disappear? This stuff just disappears and I don't understand why.
It's got to do with notation. What this is this is just indicating that this function in front of it is a derivative. Okay? And when you integrate it from the derivative back into the function, it's no longer a derivative. So you don't need the dx saying that it is.
And the 6x just goes away?
Well, in this case, the du says u to the fourth is a derivative. Okay? And as long as the du is the derivative of u, which it is, if u is 2x to the third plus 1, its derivative is 6x squared dx, then all you need to do is add 1 to its power, u to the fifth power, divide by 5, and then add the constant of integration to it. And when you do that, then you go back and you plug in your 2x to the third plus 1 in the place of u. So it's like it's adding the chain rule into what you did in the previous section. You're just still doing it by the powers. Now the one I suspect that you got stuck on because this is not actually just adding in that fraction. What this is that showing that you can check your results of doing an integration by taking the derivative of what you come up with and see if you get back what you started with. And in this case you would. If you took the derivative of that integral, the derivative of your constant is going to be 0. This is being divided by 5, so there's just a 1/5 sitting out there that's multiplying times everything, which is same as dividing by 5. And then the derivative of 2x cubed plus 1 raised to the fifth power, you bring your 5 down in front, reduce the power to 4, and then you take the derivative of 2x cubed, and that's 6x squared, and derivative of the constant is 0, so you don't put anything down for that. So that winds up being, if you multiply 1/5 times that 5, it's canceled out. So all you have left then is the 2x cubed plus 1 raised to the fourth power times 6x squared. So this is the derivative of that. And all you're doing is like it was when you solved algebra equations the first time, you could take the number that you came out with and plug it back into the equation and see if it actually did solve the equation. So that's the best part about integration, is that you can check your results. Now, where I think you probably got stuck, trying to figure out which one it is right here. Now, they actually show 2 different ways to do this, but this is example 2 by substitution. They show 2 different ways to do it. I don't usually do it the second way because I think it is confusing for students. So I try to stick with the first way. And the first way that they want you to do this is what you're looking at here, and I'm just gonna go ahead and work through it and explain to you as I go, rather than,
Because this is an in.
okay, so what we've got is the integral, and I'm gonna rearrange it a little bit before I start, so let me write it down. Let me just walk you through this step by step. Okay, now that's a little bit different from the way that it's written down in the PowerPoint. And the way that it's different is that I pull the x squared from in the front and put it over here with the dx. And the only way that I know of to handle radicals is to turn it into a power. Okay? Now when you're doing use substitutions, the things you look for are things under radicals, things that are inside of parentheses that have a power on the outside of, or things that are rational expressions where the denominator could be brought up to the numerator with a negative power, which then puts it back into something in parentheses with a power. And in this case, we've got something with a power, and that makes me think that if there's going to be a derivative here that's going to work, then my u is probably that little thing right there. U is probably x cubed plus 1. And if it is, for me to finish the problem, I need to know what its derivative is so I can see whether I've got it or not. So I look at it and I say, okay, if I get du, if that really is u, then 3 drops down in front, x squared plus 0, which actually then is just 3x squared, and dx, because that's the derivative of what u is. That's the derivative of the inside of that function with respect to x, which is why you put it down as dx. Okay? Now here's the thing. I have x squared. I have dx. What I don't have is the 3. Okay? I do not have the 3. That's a problem. I need that 3. But I can't just throw that 3 in there because that multiplies the value of the integral by 3. So it's changed it in a really fundamental way. So if I put it in here, I have now triple the value of that integral. What I can do to get it back to the original integral is multiply it out front by 1/3, because this 1/3 times this 3 is equal to 1. It brings it back down to the same unit. Okay? Does that make sense now? Now once I've done that, I don't need to do anything else with it, because at this point I've got u. I know what u is, and I have du. But in order to have it all there, I have to remember that I've got that 1/3 in front of it to keep it equivalent to the original integral.
Do you have to put the u to the 1/2?
Yes. So my u is under a radical, which is equivalent to it being to the 1/2 power. And now I've got a problem I can work on. I've got a problem I can do something with. So 1/2, I add 1 to the power. and 1/2 plus 1 is going to be 3/2. I'm also going to divide by 1/2 plus 1. And then I'm going to remember that I didn't just throw that 1/3 away, I'm going to keep it. So 1/2 plus 1 is u to the 3/2 power. You can use your calculator to add fractions if you need to, that's fine. Divided by 3/2. And that 1/3 still out there. So if I multiply straight across, because this is just multiplication, fraction times fraction, 1 times u to the 3/2 power is u to the 3/2 power. 3 times 3/2 is 9/2. And then u to the 3/2 power divided by 9 over 2 is the same as u to the 3/2 power times 2 over 9. Because this is division. And when you divide by a fraction, you flip what you're dividing by and then you multiply. So that means then that what this finally actually looks like is u to the 3/2 power, and the 2 is going to go in front of it and the 9 is going to stay on the bottom. And now I'm just going to go back and plug back in what u originally was.
Okay, so there again, then you keep the 1/3, but you do away with the 3x dx.
Because it got absorbed into being what du was.
Oh my God, okay, whatever.
Okay, what you have to keep in mind is that this is du.
So you slide it down just a little.
That's du.
Right.
And this was u to the 1/2 power.
Right.
So when you rewrite it down here like that, this is du. It just goes away. That's what it is. It's been replaced by its substitute. It just disappears. So then the very last step that we do is we go put u back in. And remember, u was x to the 3rd plus 1. So this is 2 times x to the 3rd plus 1 over 9 plus your constant of integration. You always have a constant at the end.
So you have to do to the 3/2.
Hmm?
3/2. Since you're doing u to the 3/2.
Yes, I left out my power, thank you. So does it make sense now why if you put a number, a multiplier in, that you have to put the reciprocal of that multiplier out front? Because that way they cancel each other out.
I see it in reciprocal, I just didn't realize, and now, because it was just going away, I guess, and there's no reason why, okay. So it just disappeared. That was my question.
Okay. Now the other way that they did it, because this is exactly what I just showed you, is they talk about using it that way. They say if you let you let u be x cubed plus 1, then du is 3x squared dx, and you only have 1/3 of du. So you multiply your integral through by 1/3 to get the rest of du. Somehow that never clicked for me, and I don't think it's ever clicked for any student I ever had. You know, where did this magic 1/3 come from? It came from the same place it did in method 1, but it just doesn't make sense the way they explain what they're doing with it. This one at least you can see, well, okay, I need to have 3x squared, not x squared. So I need a 1/3 and a 3 so that they'll cancel each other out. Now the only thing that you have to be careful of here, and this is an important caution, what I showed you in that example will not always work. None of the problems in that section of homework won't work. They will all work. But just so that you realize there are other situations where this U substitution will not solve the problem. There's other techniques of integration, and we probably won't even address those in this class because you're not likely to ever need them. But the thing that, you know, you may see one and say, well, can I just do this? So if this problem, instead of having x to the second as part of the dx, if it had x to the third sitting there, well, that means that if u is x to the third plus 1 and du is 3x squared, I could get a 3. I can multiply by 3 and 1/3 and cancel it all out and everything's good. Life's happy. But I can't get an x to the third. I can't just take an x out and throw it away. Well, because we don't know what the value of x is, so we wouldn't know what to divide by or take the reciprocal of to be able to put it in. You can do it with a constant because you know the value of the constant. You don't know the value of x. It's a variable. And I put this in, and actually this is not totally straight out of the book, it's close. But I find this to be good advice because I remember sitting where you are and struggling to try to figure out what is u. How do you decide what's u? And what you want to remember is that u should equal some expression in the integral that when you replace it with u, it tends to make it look simpler. And the other thing is that it has to be an expression whose derivative, outside of a constant like 3 or negative 12 or 5 or something, outside of just a single coefficient, that you actually have the derivative inside the integral already. You can't add any variables inside the integral. And this one mentions in example 1, we could have chosen u to be 3x squared, but choosing it to be 3x squared plus 4, everything that's inside the parentheses is better because that's more of the derivative. So let's look at another example. Because I really think the only way to actually get this is to just keep doing problems.
The one in my math lab it came up with a negative, and maybe I just missed a sign or had it wrong.
Well, at this point, since I think we've answered your question, let's go look at the one in my math lab.
Because you had to multiply it by something, then multiply it by the fraction too. You had to do both on this one. If that makes any sense.
Do you remember which one it was?
Number 4. That's just going in.
Okay, let me work it through step by step and explain yours to you. And this one's like the one I was just looking at, so this is just as good as the one I was going to do. Did you have a question on that same one? Your numbers may be different, but it was that same kind of problem?
Yeah.
Okay, well, follow along with this and just realize that your expression is going to be different, but that the process is going to be the same. So the first thing we're going to do is we're going to look at this and say, well, you know what? This looks, and this is my English way of saying it, my non-math way of saying it. This looks a lot less complicated to me than this does. This looks like something I would have had to do chain rule on. So if it is what I should be using, then I'm going to try to let that be u. And notice that when you pick out u, you don't keep the power. It's just going to be the inside of it. But I need the derivative of the inside of it just like I would if it was chain rule. So the derivative of what was inside would be 2 times 2 is 4x plus 14. And I'm looking up there and saying, I don't see 4x plus 14. But then I think, well, you know,
So you always look for that DU in the problem somewhere to
Yeah.
try and make it similar.
and try to make it into this.
Exactly, okay. make it
Okay?
exactly.
Now,
Two.
I have something that might work here. Once I've got that, I realize that this is what I've got. And this is what I need. I mean, the dx, yes, I need dx out there, but I can write dx all I want to and not change anything. But I don't have 4x plus 14, I've got 2x plus 7. But 2x plus 7 is a factor of 4x plus 14. So there's where the 2 comes from. So that means what I need in order to have du in this problem is I need that 2. So I'm going to put the 2 here. But now when I put a 2 inside, I have effectively multiplied everything that I'm integrating by 2, which changes the value of it. So I need to also multiply it by 1/2 to change it back to what it originally was. And now that I've done that, then I can rewrite the problem as the integral, and I'm going to rewrite this with a negative power. The integral of u to the negative 4 du. And this is du.
I didn't change it, so I didn't make it a negative while I put on the bottom. That was how they had said to do it.
Yeah, but that,
Which, I mean, that's probably maybe with a negative. Keep going, because I don't.
okay. So I changed it to a power because I don't have a rule that says how to do 1 over something. The only thing I have a rule to do 1 over something is if it's 1 over x. This is not 1 over x. It's 1 over something to the 4th power. And I don't have a rule to do something 1 over something to the 4th power. But I do if I change it to the negative 4. I have something I can do with the power that's negative. I have a way to do the integral. The only thing you have to be careful of is that you don't forget that you need that 1/2. That's still part of your process now. So what I have here, this is the equivalent integral. That's equivalent to what I changed it to. This and this are really the same thing, except I'm not writing down what u is. And then I'm going to apply the power rule to that. The power rule says take u, add 1 to its power, divide by the new power, and don't forget to keep that 1/2 coming. So this is going to be 1/2 times u to the negative 3 power divided by negative 3, which is equal to 1 times u to the negative 3 is u to the negative 3 over 2 times negative 3 is negative 6. And now all I need to do is put back in my u, substitute back in what u was. And u is 2x to the fourth plus 14x. And then I add my constant on the end because you always have to add the constant. Okay?
It's x squared, right?
Do,
In the parentheses.
It's mostly on board.
yeah, it is, it's 2x squared, sorry.
And what's underneath, is it still?
-6.
Negative 6, because
Okay,
that's
so
2
negative
times,
6 can- okay. I
yeah,
understand.
that comes from 2 times
Okay.
negative 3,
Here we go. Okay.
okay?
So can we just, well, link that in the, because I had it labeled.
You worked it out probably just exactly like they did.
Oh, yeah, I mean, I followed it step by step.
But all they did was they dropped it back down in the denominator.
Well,
And
they never took it out of the denominator, they just left it in. Which it comes up with the exact same answer.
it does come up with the exact same answer. I haven't looked at the way they would explain it, but the way that we've always done everything we did in here was if it was in the denominator and we could do it, we'd bring it up to the numerator with a negative power to make it easier to work with.
Mine was, the negative in that was really throwing me off too, and that's just where they left out some steps, and with that, we subtract.
Okay.
So that's good.
Okay, is there any others anybody wants to look at?
I had trouble with number 3.
Okay. Go back to the grade book. We'll work 3 and 4. So we've got the integral of 12 over 2x minus 9 to the 7th power dx. So here we've got a constant. And this looks like it probably would be a good candidate to be u. So if we use this for u, then du, the derivative of 2x is 2, the derivative of negative 9 is 0, so du is just 2 dx. The derivative of that with respect to x. Now, I need 2, but I got 12. I don't want 12, but I'm stuck with it. I need to somehow turn that 12 into a 2. Does that make sense? How can I turn 12 into a 2?
This is a problem.
I put 1/6, because 1/6 times 12 equals 2. So that 1/6 will take care of that, but now I've reduced the value of this integral to 1/6 of what it used to be. So again, I'm just going to flip it over, take the reciprocal, and multiply in the front by 6. That's why you don't always multiply by a fraction. Sometimes you have to divide to get your constant. So then you multiply in the front to put it back. Okay? So now what my integral actually looks like is 2x minus 9 to the negative 7 power, because I'm going to bring it up to the top so I can do something with it. And then 1/6 times 12 is 2 dx, which is what I want. So now what I have is u to the -7 power du. Just make sure I bring down my 6. And then my derivative rules say, to finish this then, I need to take 6 times u to the -6 power, because when you add 1 to the 7, it becomes -6. And then I need to divide by -6. And doing this is what actually makes that disappear, because you are anti-differentiating that and taking it back from a derivative, which was this, to a parent function that was not a derivative, an antiderivative. And now we have a little bit of cleanup we can do. This 6 cancels out that 6, but it doesn't cancel out the negative sign. So now I've turned it into -u to the -6 by canceling out the 6's. And now I can go back and put in my u, which was 2x minus 9. So this is 2x minus 9 with a negative sign in front of it, raised to the -6 power, plus a constant. And you don't have to put it back in the denominator, but if you want to, you can. You should be able to enter that in and get the right answer if you want to go ahead and try that.
That was way off.
Does this make sense? Can you?
Yeah, much more than their instructions did.
Well, that's why I didn't necessarily instruct you to follow their instructions and did the video for you in Shobi, because I did all my whole 15.2 lecture is in Shobi, and I did it with Explain Everything, I think was the name of the program I used. And I do them this way.
Yep, they like that.
Okay. So let's look at another one.
Let's do one of those E ones. I hate that.
I may have to poke around here for a minute and find one. Let's see.
Well, there's one on number 5. I think that is,
Okay.
that's an exponent raised to an exponent.
Okay, we've got the integral of 3x squared e to the 5x to the 3rd power dx. Okay. If I've got something like this, and I think Tarina can probably agree with me on this one, e to some ugly looking power is always a lot more complicated looking than something like 3x squared. In fact, you put an e to the anything in there and I always think that's more complicated. Okay? So I'm going to say, you know, maybe the u is in here, but you can't turn e itself into the u because e is a number raised to a power. So actually what the u is in this case is probably its power. Because I have a way to do an integral of e to the u, because the integral of e to the u is e to the u. And the derivative of e to the u is e to the u, okay? So it's the power that I'm worried about. So if the power is 5x to the third, then what would be its derivative? And that's right, it would be 15x squared and then dx, because this is a du derivative, so I need to make sure that I'm putting it back in terms of x. Okay, well, I don't quite have 15x squared dx. I've got 3x squared dx. I need to turn that 15 into a 3. And I can turn that 15 into a 3 by dividing that whole thing by 5 or multiplying it by 1/5, which is the same thing. So if I want to have du, what I'm going to have to do is I'm going to have to actually multiply this times 1/5, which means on the outside, I'm going to multiply by 5. Whatever you put inside the integral, on the outside you put its reciprocal.
Wait, 1/5 on the inside? I thought you had to make that. I was writing.
Oh, wait. I wrote it back. I'm sorry. I wrote it backwards, I think. Wait.
When you multiply by 5 and then divide it by 1/5 on the outside, I thought you had to make
You have to make,
that up there look like your du.
yes. I just said the whole thing backwards. I'm sorry.
Please don't.
If you could figure that out, Karina, you weren't that confused.
No, I had it written down, why, on mine, so I was looking at what I, and I knew that was backwards.
Okay, now, yeah, if I put the 5 in, I have my 15x
Right,
squared,
right.
and then on the outside I have to multiply by 1/5.
Okay.
So du is the 15x squared, and now I've got e to the 5x to the third power, and 3 times 5 is 15x squared dx, as long as I put 1/5 on the outside. So now I have 1/5 times the integral of e to the u du. Well, it's part of du. So what is the integral of e to the u? It's e to the u. And what was u?
Five x to the third.
Plus 3, plus c. And if you don't want to do the fraction, you can write it this way. You can put e to the 5x to the third and just put the 5 underneath it plus the constant. But either one of those should work in my math lab. Okay? Now that, yeah, you've got the right answer on that one. Let's see. Let's look at number 8. We've got the integral of x over the square root of x plus 7 dx. And I would rewrite that at the very beginning by calling that x plus 7 to the 1/2 power so that I can deal with the power rule, because that's the only rule I've got that I know of right now. And make it negative because I brought it up out of the denominator. And then have x dx out here. So now I don't have the fraction. And if I let u be x plus 7, then the derivative of that is just 1 dx. So I have a problem. Because there's an x in there, and I don't have any way to get rid of it. Right? Yeah, but I don't know what the value of x is to know how to carry it along as a multiplier. So we can't put in just an x. We're kind of stuck. I'm interested to see how they explain this one. I know how to do it. I want to see how they explain it.
They solve for x.
That's what you should do.
Yeah, that's what I did.
Okay. Yeah, they're presenting it correctly. Although it's not intuitive, that's how you should do it. So what you have to do is you have to go back, since I don't have du.
We did on that other screen.
Oh, sorry, I forgot to close this one down. So what I do is I say, well, x is equal to u minus 7. So then this integral becomes u minus 7 over the square root of u minus 7 plus 7 dx. It's just being substituted in.
See, because they put in ours that du is equal to dx.
Well, in this case, du is equal to dx because du is,
X.
well, no, du is actually just u. It actually does equal just x.
Well, they had dx. Du is equal to dx.
Oh, yeah.
Like it was up there.
They are equal because we did this and we're taking the derivative of this, which is du, and the derivative of this, which is dx. Actually, it's 1, but it's 1 dx, okay? Because that's what it is up here. So now I'm able to do this problem, even though it looks pretty ugly, because what this is u minus 7 plus 7 to the negative 1/2 power times u minus 7 And du and dx are the same, so that's actually du. du. And this almost always happens when you do this. You have u to the minus 7 plus 7, so that really is only u to the 1/2 power, because minus 7 plus 7 disappears, times u minus 7, and there again we still have du out there. And then you're going to actually multiply this out. So u to the 1/2 times u to the 1 remember what you do is you add the exponents. Minus 7u to the negative 1/2.
How did you go, I'm confused how you went from the 3 and the parentheses, the u minus 7, oh, those canceling out.
Yeah.
Okay, and then that will actually drop. Okay.
Okay?
Yeah.
So do you see how I got u to the negative 1/2 plus 1? Okay.
That's, yeah, that's good.
Because I'm multiplying u to the negative 1/2 power times u to the first power, and when you do that, you add the exponents. And then u to the 1/2 power times negative 7 is negative 7u to the 1/2 power. And both of these are now power rule problems. Negative 1/2 plus 1 is 1/2 minus 7u to the negative 1/2. It's still negative. So there's my integral, and there sits du.
Do it over the half, you have to do that, add that 1 on top, then you have to do that on the bottom,
What do you mean?
where you did the u to the negative 1/2 plus 1. So you're just distributing that out, you haven't, why did you add, because of the 1 inside, for instance?
Right.
We're not putting them together, okay, we're not doing the other little bit.
So right now, all we're doing is we're trying to get the integral into something we can do a power rule on. Okay? So now you can integrate this term by term. So when you take this and you turn it back into what that derivative came from, you take u and add 1 to its power and divide by that new power. Then subtract. No, it's not negative 1/2, it's positive 1/2, okay? And then when I do this part, I carry along the 7. That's u to the negative 1/2 plus 1. Divide by negative 1/2 plus 1. And then go back and remember that 1/2 plus 1 is 3/2. And negative 1/2 plus 1 is 1/2. So this is u to the 3/2 power divided by 3/2, which is multiplying it by 2/3. Minus 7u to the 1/2 power multiplied by 2. Which is going to make the whole thing then 2u to the 3/2 over 3 minus 14u to the 1/2. Yeah, this one's a doozy.
Is there anything you think is complicated on the day of the final?
Not on the final, because I tried to keep the final pretty clean. I don't think there's one that's complicated on the test either, though. I'd have to go back and look, because I haven't looked to see exactly what all's on there yet. So now that we've got it down to where we're all we need to do is plug u back in. Remember that u was x plus 7. So then this all becomes two times x plus 7 to the 3/2 power divided by 3 minus 14 times x plus 7 to the 1/2 power. And you don't have to turn that back into radicals. My math lab ought to take it as powers, but if you want to turn it back into radicals, you can. Okay? That's probably the longest one on there. And the really sad part about that is when you look at it at first glance, it looks like it's going to be easy. It looks like it's pretty simple until you figure out that you have to make this u and then solve u for x and put it back into the problem for x. Oh, and yes, there is. There's one thing that my math lab would kick you out for, and that's not putting that constant on there. But I never put my constants on until the end. We okay? And that's what I was looking to see if there was one.
Number 9, number 10.
That's just an application problem. It really does. This one's probably harder to do than number 10 is, so we'll do this one. Okay, so here's what we've got. And I don't think there's anybody in here that wouldn't tell me that this looks like it ought to be u. So if it's u, the question is, what's the derivative? So du would be 0, because the derivative of 1 is 0, plus 12, and the derivative of the natural log of x is 1 over x, right? And you might be tempted to write it that way, but I think you actually want to keep this like it is. Because if I can rewrite that integral, I have 1 over x. Agreed? Since I'm dividing that by x, I can also multiply it by 1 over x. So this is equivalent to this. So I have that much of du. I don't have the 12. So I put in 12, and I put 1/12 out front. And now I have DU. Does everybody see what I did? So now I've got it in a format I can do something with. That's equal to 1/12 times u to the 11 plus 1 is 12th power divided by 12. So that's equal to 1 times u to the 12th is u to the 12th. 12 times 12 is 144. And now I can put u back in. How did I?
I think the 112 carried over, you, is that you to the, is that the 11?
Yeah, that's to the 11th power. Okay?
Can you slide down just a second, see if I, because I wrote most of it.
Yeah, it does look a little bit like a 4. It actually, it's an 11 though.
Okay, that's where I couldn't figure out where that came from.
When you're doing this kind of a problem, what usually happens is that the number in front winds up multiplying times itself or somehow canceling out, one or the other. So now if I put u back in, remember u is 1 plus 12 ln x. Oh, it's pouring down money. There's your final answer. It's all wrapped up in that the derivative of the natural logarithm of x is 1/x. And the derivative of the natural logarithm of a function is 1 over that function times the derivative of a function. So there could be a u substitution that way too. But I think that's probably gotten an example of just about everything you're going to run across now. So, y'all do y'all need to take a short break or shall we go on? Okay, take a short break and I will set up for the next couple of sections.
We're going on to 15.3, is that right?
15.3 and see if we can get any of 15.4 in.
Are you gonna load it in Shelby or D2L?
Probably both. I'll probably put them like I have been the others, just put them in D2L if you want to print it, or in Shelby if you want to fill it out in Shelby. It's up to you.
I just sent that in hand. Can you download that where we can print it right now, so we can have it when we
Yeah.
go over it? So the test is gonna be on 1 through 5. So if we only.
Actually, we're not going to do all of any of the other sections, any of the later sections. We're going to do little parts of them.
Okay.
And based on what I'm seeing on the test, I'm trying to put things on there. There's maybe one problem out of chapter 12, one, take this derivative. You know, because I don't want you to forget how to take derivatives while we're doing this. And there's a couple on there that I know are really similar to something that's on the final. Because I'm trying to keep that study guide built in. So there's a little bit out of chapter 12, a little bit out of 13, and then the test is about half chapter 15. Let's see.